dan jitu, penuh bervisi guru AYU, mencapai misi yang satu, permisi kita bantu.
Tahniah. Siaran langsung ini dibawakan khas kepada anda oleh Akademi Youtuber Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hai, Assalamualaikum, salam sejahtera dan selamat malam semua. Kita mulakan dulu kelas kita pada malam ini dengan bacaan Ummul Kitab dan Al-Fatihah. Bagi yang bukan beragama Islam, anda bolehlah bertafakur mengikut kepercayaan masing-masing. Al-Fatihah. Indah berbalam si awan petang berarap jadilah pohon ara. Selamat datang pemanis kalam, selamat datang awal bismillah, pembuka bicara bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Sekali lagi selamat datang cikgu ucapkan kepada anak-anak murid yang dikasihi sekalian di mana jua anda berada dari serata Malaysia. Cikgu doakan anda sentiasa sihat walafiat. Okey, kita ada Jimmy di sana. Hello Jimmy, thank you for joining us tonight. So untuk anak-anak pelajar, cikgu ada sediakan nota dalam bentuk PDF untuk kelas pada malam ini. So anda boleh muat turun, boleh cetak keluar untuk rujukan anda. Okey, boleh cetak sekarang kalau ada printer di rumah. Kalau tak ada tak mengapa. Tengok dulu kelas ini, nanti boleh cetak kemudian dan tonton semula video untuk mendapatkan jawapan yang penuh. Okey, jadi seperti biasa malam ini kita akan bersiaran untuk kelas siaran langsung tuition online percuma yang dibawakan oleh Akademi Youtuber Malaysia dengan inisiatif dan kerjasama Kelab Guru Malaysia dan EDD Malaysia. Jadi anda boleh tonton secara live daripada YouTube saya. Siapa yang belum subscribe, bolehlah subscribe channel Cikgu Hasnitah untuk memberi sokongan kepada cikgu yang telah subscribe. Terima kasih cikgu ucapkan kerana terus setia berada di channel cikgu. Semoga segala video perkongsian yang ada di channel ini memberi manfaat kepada semua yang mengikuti. Jadi pada malam ini kita akan mengikuti kelas fizik untuk tingkatan 5 untuk bab 4. Untuk kelas DLP, tajuk dia 4.1 Force on a Current Carrying Conductor in a Magnetic Field. Okey, jadi kalau anda sudah bersedia, cikgu pun tidak ingin membuang banyak masa. So mari kita teruskan dengan kelas pada malam ini. Okey, before that, this is our schedule for this week. We only have one class conducted for this week for Form 5 classes entitled 4.1 Force on a Current Carrying Conductor in a Magnetic Field. So disampaikan oleh saya sendiri, Cikgu Hasnitah, kini berkhidmat di SMK Bagan Jaya, Butterworth, Pulau Pinang. Okay students, so yang belum lagi muat turun aplikasi kita di Android anda boleh muat turun sekarang aplikasi yang diberi nama Akademi Youtuber Apps. Okey, apa yang ada dalam apps ini? Ada puluhan ribu video yang anda boleh gunakan untuk membantu ulang kaji anda. Kita ada video yang dihasilkan oleh sukarelawan AYU dari seluruh negara merangkumi subjek-subjek dari pra-sekolah sehinggalah universiti, dan apps ini juga telah banyak memenangi inovasi di peringkat kebangsaan maupun di peringkat antarabangsa. Okey, jadi untuk malam ini, so cikgu mulakan dengan perbincangan kita. So I begin with our discussion tonight with 4.1 Force on a Current Carrying Conductor in a Magnetic Field. So student, along with the discussion, you may ask a question and also you can respond to the question I show you on the slide. Okay, so I hope this session can be a two-way communications, then it will be more effective then. Alright. Okay, so this topic is covered in your textbook from page 136 until page 148. So you may be ready with your textbook as well, student. Again, I would like to inform you, you can download the PDF copy for this lesson just for free from the link I share here on the pin messages. It is also provided on the video description below. All right. Okay, so what do we have in this first content standard of chapter 4? So there are a few learning standard. We altogether we have 5 learning standard. Okay, before that, let us take a look at this short introduction on these topics. If you look at the GIF day, and there is a why there. How does an electric motor works? Okay, so table fan is operated due to electric motor inside. So the big question there, how does electric motor work? So the work of electric motor will be studied in this subtopic 4.1. Okay, students. This is another examples of daily instrument or devices which works based on the current carrying conductor in a magnetic field. Okay, before that, can you respond to me? Can you hear me clearly, students? Am I sound clear to you? If you do, please give me some response by typing yes. Okay then, students. Okay, so this will be our a current carrying conductor in we have here. So for the first activity, you can check this from your textbook as well. Okay, this is activity can be conducted in school to study the effect of current carrying conductor in a magnetic field. Current carrying conductor refers to a wire, okay, which plays in between a magnetic field with a different polarity, as you can see in this arrangement of apparatus. Okay, so from this activity, when you place a copper wire here in between this magnetic field, and when we switch on the current supply, you will see the copper wire will move to a certain direction. As shown in this video, student. Okay, I play the video again so you can see how the copper wire moves. This is the initial position. So after the switch is turned on, so you can see the direction. Okay, so how to determine in which direction the wire will move will be discussed in this lesson. Okay, for example, let's say this is the example of result that we get from this situation. So if you look from the connection, the current, let's say the current flows in this direction. Okay, when the current flows in the circuit, so you will see the copper wire move to the right. Okay, and later when we reverse the direction of current, the copper wire move to the opposite direction, which is to the left. Okay, and when we do the third situation, we reverse the polarity of the magnet. We maintain the direction of current, but we reverse the polarity of magnet. Then the copper wire will move to the opposite direction, to the left. Okay, while what happened when we place a copper wire parallel with the direction of current, now you will see there is no movement shown by the copper wire. Okay, so this is the few example of question we can ask according to this activity. First, they ask, is there a magnetic field in the region around the short copper wire before the current is switched on? Okay, what do you say? Any magnetic field around the short wire before the current is switched on? So the answer is No. Okay. The copper wire will only experience magnetic field around it when we supply current across it. Then it will turn into electromagnet. Okay, students, what is electromagnet? It is a temporary magnet where a conductor becomes a magnet when only current flows through it. Alright? Okay. So second question, they ask, name the two sources of magnetic field in the region around the copper wire when the current flows. So the magnetic field is coming from two sources. The first one is the magnetic field between the two permanent magnet. Second, magnetic field around the current carrying conductor. Alright. Okay, so this is the third question asked for this activity. From your observation, just now you see the short video. What makes the short copper wire move, student? So what actually made the copper wire move in this activity? That is due to the production of force. Yes, from the interaction between the two magnetic field. Magnetic field from the permanent magnet and magnetic field from the current carrying conductor. So when they interact, they will produce catapult field where it will result a force acting on the conductor. Alright. And what law relates the direction of force, current, and magnetic field in this study? Okay, can you give some response, students? What is the name or state the law applies here? Okay, which relates the direction of force, current, and magnetic field on the current carrying conductor. So the name of the law is Fleming left hand rule. Okay, so Fleming left hand rule. So how to understand Fleming left hand rule? It is very simple. Okay, you apply the first three fingers on your left hand. So everyone, you can take your left hand. So our thumb, okay, the thumb represent the direction of force. In which direction the wire will move to. Okay, this will be the product, and our first finger represent the direction of magnetic field. Our index finger, it always pointing to the south. All right, and your middle finger indicates the direction of current flow across the conductor. So the rule named as FBI, easy to remember. FBI. Okay, force, magnetic field, and direction of current. Later, we will check on a question how to apply this rule. All right. Okay. So you can complete statement number 5, number 6, number 7 in your module number 8 and number 9 as well. Okay, so the fifth question here, what is the relationship between direction of magnetic field, the current, and the force acting on a conductor? So if you notice all these three fingers, when you apply them, they must be perpendicular to one and another. Okay, these three hands must be perpendicular to one and another. Okay, so the answer, it must be perpendicular. Before that, you can complete the blank spaces. The quantity represented by each of these fingers in Fleming's left hand rule. All right. Okay, question 6 there. Explain why the wire does not move when the direction of magnetic field is parallel to the direction of current. So imagine if these two are parallel. So now they are parallel, which means no force will be produced. Okay. So no force produced when they are in a parallel position. What is the difference to the motion if the wire supply with a stronger magnetic use in these studies? So, which means we provide stronger magnetic field. So definitely the force will be increases. So the wire will move further distance. Okay. And second, if we increase the current flows across the conductor, again, it will create or it will produce a bigger force on the conductor, so it will move a further distance. So from here we understand the strength of magnetic field and the magnitude of current flow across the conductor affect the magnitude of force acting on the conductor, right? Okay. So what is the conclusion we can say about this first activity? In what situation does a force act upon a current carrying conductor? So how to answer? So we understand from the activity just now, the force will be act upon a current carrying conductor when we place the current carrying conductor in a magnetic field. We place the wire or the conductor in between a south and north pole. Okay, magnet. Second, this is the condition where the magnetic field must be perpendicular to the current flow across the conductor. Okay, students, so by here, we can say the direction of the force depend on the direction of the current and the direction of magnetic field. So these are the two factors affect the force acting on a current carrying conductor. First is the magnitude of current. Second is the strength of magnetic field. Okay, for example, if you look at this arrangement, when current flow from this positive terminal along the wire, so the current flow to the front from B to A. So how to place our finger here? So your middle finger should point outwards, pointing to yourself, okay? While our index finger pointing downwards, okay? Pointing downwards. So you will see that your thumb will be pointing to the right, which means finally the copper wire will move to the right direction. Okay, we also have Putri Alia with us. Okay, welcome Alia. Thank you for joining our lesson. We're still in the first learning standard. Okay, to understand Fleming's left hand rule. All right. Okay. Okay, next student, what do we have in the next slide? Okay, now we are entering the second learning standard. Okay, this is the most important part for you to draw the pattern of the catapult field. This is to indicate the direction of force acting on a conductor. Okay, students? Okay, now let us check on these two diagrams. So what is catapult field, student? What is catapult field? So catapult field is a resultant magnetic field. Okay, it is a resultant magnetic field which produced from the interaction between the magnetic field from a current carrying conductor, the wire, and the magnetic field from the permanent magnet. For example, in the first diagram, this is the position of the permanent magnet, north pole on the left, south pole on the right. So the magnetic field will be directed to the south. Okay, from north directed to the south. The blue arrow represent the magnetic field on the permanent magnet. And here you see there are dot symbol there. Okay, dot symbol there shows to you that the current flows out of the conductor. So current flows out of the conductor. So when the current flows out of the conductor, the magnetic field around the conductor will be anti-clockwise. Okay, in anti-clockwise direction. Okay, so if you look at the region on top, the blue arrow and the green arrow are in the opposite direction. Okay, means the magnetic field in the opposite direction. So it will produce weaker magnetic field on top. Okay, while at below, the direction of magnetic field between the permanent magnet, the blue arrow, is now equal, same, in the same direction with the magnetic field around the conductor. So it will produce stronger magnetic field at the bottom. So the difference of these two, the strength of magnetic field above and downward will create a resultant force which is acting upwards. Okay, so this is how we draw the resultant magnetic field or the catapult. We draw more number of line below the conductor showing that stronger magnetic field below. So it will push the conductor in an upward direction. Okay. So if you apply Fleming left-hand rule here in this catapult field, so how to place our finger, the dot mark showing that the current move outwards. Okay, so your middle finger should point to yourself. Okay, and our index finger pointing to the right. Okay, pointing to the south. So you will find that your thumb will be pointing upwards, which means the force acting on the wire will be directed upwards. So it will move the wire upwards. All right. Okay, so that is catapult field. Okay, students. So now the second activity is to describe how a current carrying conductor in a magnetic field experience a force. So you can try to find a paper, a blank paper and a pencil, and you can draw the direction mark and label with B the direction of magnetic field. So can you tell me where is the direction of magnetic field? We place north pole magnet on top, south pole magnet below. So remember, magnetic field always pointing to the south. So you can label, okay? You can label the magnetic field, the blue arrow with symbol B. B is a symbol for magnetic field. So it pointing downwards to the south. And then what happens, student, when we close this switch, which means current will flow in the circuit. In which direction you can check the polarity of the terminal of the battery. So current will flow in this direction. Okay, when we close this switch, so current will flow in this direction. So along the copper road, it will in that direction. Follow the green arrow, okay, to show the direction of current. Okay, so current will flow into, okay, into the paper. So finally, what happened to the copper road? It will move to the left. Okay, so how to check this direction is correct? So we can apply Fleming's left-hand rule. Okay, so you can take your Fleming left-hand rule. So you bring your index finger pointing to the south, pointing downwards. Okay, you can do them now. Okay, follow me. So put your index finger pointing to the south, downward. And then your middle finger, direction of current, okay, flow into. Okay, so it flow into, so it's like this. You point it on the paper. So now you'll find your thumb will be pointing to the left. Okay, pointing to the left. So it shows the copper road move to the left direction. All right. Okay, so I hope you can try this at home later. So make sure your finger, your wrist can be turned 360 degree to understand Fleming's left hand rule. So are you doing good so far? If you do, you can type okay in the live chat there. And we can try to complete the third diagram. Okay, draw on diagram below the magnetic field produced by the permanent magnet and the magnetic field produced around the current carrying conductor. So for this one, very easy. It is always directed from the north to the south for permanent magnet. Okay. And for current carrying conductor, student, now you see there is a cross mark there. See? Cross mark. Cross mark tells us that current flow into the paper. okay, along the conductor. So when current flow into the paper, so the direction of magnetic field will be clockwise. Okay, it will be clockwise. So how to know clockwise or anti-clockwise? Actually, here you can apply a right hand grip rule. Okay, right hand grip. So you can take a pen. Okay, for example, you can take a pen. Okay, you can take any straight object. For example, let's say this is the conductor. It says current move into. So how to hold? So your thumb move into, okay, pointing into the paper. So you will see your four curl finger will be curled in a clockwise direction. In a clockwise direction. So that's why we draw the direction of magnetic field in a clockwise direction. So apply right hand grip rule for conductor. Okay. And when we combine them, what will be the result, student? Okay, so from our discussion earlier, so what will happen when we combine? So you will find on the left side, the direction of magnetic field is opposite. Okay, for the permanent magnet, it is directed downwards. While for the conductor, it is directed upwards. So we understand weaker magnetic field produced on the left side. Okay, on the left side, it produces weaker magnetic field. While on the right side, the direction of magnetic field for permanent magnet is downwards. And for current carrying conductor, it is also downward. So same direction. So this area or region produce a stronger magnetic field. Okay, so from here, how to draw the catapult field and in which direction the conductor will move. So when you join them, so this is what happened. So stronger magnetic field on the right side, weaker magnetic field on the left side, which means the conductor will be pushed to the left. Okay, so force will acting to the left from the stronger magnetic field towards the weaker magnetic field. All right. Okay. And the rule to determine the direction, yes, we apply Fleming's left hand rule. Okay, you can place your finger here. Now you see X mark there. So your middle finger should point into the paper. Okay, into the plane. And you twist your index finger, it should pointing downwards. So now your thumb will be pointing to the left direction. All right? Okay. Okay, this is the following question refer to this activity. What will happen to the motion of copper rod when the rheostat is adjusted until the resistance decreases? Student, what happen when resistance decreases? It means the current will be higher, right? So just now, higher current, higher force will be produced. So the copper wire will move further distance. And second, what happen now if we change the battery to AC power supply? Battery is a direct current. The current flow in one direction. So the force will move in one direction only, which is to the left, according to the diagram we draw just now. But now if we change the battery to AC power supply, AC power supply mean the current flow in two direction alternately. So what do you think will happen to the force? So definitely the force now will be changing alternately to the left and right, to the left and right. So this can cause the copper wire vibrate or not moving at all because of the fast changing of the direction of current AC. So you will see it either vibrating or not moving at all. Okay, when the current changing terminal in flowing. All right. Okay. So next, this is the conclusion we can make for the second activity. Okay, so there are four conclusions we can understand there. First, when we turn on the switch, so what happened? Current flow through the short copper wire and produce magnetic field around it. So the wire will become electromagnet. Okay, then what happened? There will be an interaction between the magnetic field produced by the current carrying conductor and the magnetic field of the permanent magnet. And this interaction will produce a resultant magnetic field which is called catapult field. So as the effect, resultant force will be acting on the conductor. So you will see the short copper wire move to a certain distance. And how to determine the direction? By applying Fleming's left hand rule. Alright? Okay. Next. Okay, so let us test your understanding on what we discussed just now on catapult field. So again, we have a magnet here. Permanent U is for north. Okay, we place permanent magnet here. North polarity on the left, south polarity on the right. So you can draw the magnetic field in between this permanent magnet. So yes, okay. And we place a current carrying conductor there where it shows X mark. X mark mean the current flow into paper. So the direction of magnetic field around the wire will be clockwise. Okay, into paper will be clockwise, out of paper will be anti-clockwise. Okay, and here is the catapult field, the combinations or interaction between these two magnetic field. Okay, so we draw, this is the magnetic field direction for the permanent magnet from north to the south. All right. And for the current carrying conductor, it shows X mark there, showing that current move into the paper. So direction of magnetic field is clockwise. So when we combine this, what happened? So a stronger magnetic field will be produced on top because they are moving in the same direction to the right, and weaker magnetic field will be produced below because of the opposite direction of both. Okay, so a resultant force will be acting on the conductor downwards. Okay, so this is how we draw the catapult field. Okay. Okay, then students, now let's enter the third learning standard to explain factors affect the magnitude of force on carrying conductor. So actually, I have stated this factor earlier. Okay. So what are those factors? It is discussed in this experiment 4.2 taken from your textbook. So we have diagram there. It shows two table fan with a speed adjusting button, as you can see there. From this diagram, you can see that the first fan on the left rotate with a lower velocity, while on the right, the blade is rotate with a high velocity, high speed. Okay, so first, what is the inference we can write for this experiment? Current influence forces. So we know the manipulated variable according to this diagram is the magnitude of current. Okay. Hypothesis, the larger the current, the larger the force acting. So aim to study relationship between current and force. So our MV, as I mentioned, the current, our RV, the distance travel of the copper wire. This is the apparatus conducted in the laboratory. And our fixed variable is the number of magnet. So we keep constant the strength of magnetic field. We study the magnitude of current. So it will affect the force acting, which is shown by the distance travel of the copper wire. Okay, so this is the setup of the apparatus. Okay, let's say we conduct the experiment with this magnitude of current. Started with 0.5 and increases to 2.5. So if you understand our discussion, when the current increases, the distance of the conductor displaced also will be increases from 0.5 until 2.5 ampere. All right. Okay, so what conclusion we can write? The larger the current, the larger the force, therefore the further distance traveled by the conductor. Okay, so discussion follow. What caused the copper rod move? Okay, so it is due to the resultant force produced by the catapult field. Okay, why the current supply cannot be connected for a long time on the copper track? So this is uh, critical thinking. Okay, you have to think why we cannot supply the current continuously. So this is to avoid temperature rise on the copper wire, which can cause heating, and we afraid it can lead to fire. Okay, so what will happen if the number of magnet increase? So if you understand, when we increase the magnet means we increase the strength of the magnetic field. So what will happen? The conductor will move or displace at a further distance. All right. Okay. Okay. So students, what if we take a short break for a while? Don't go away. So we will back after. Okay, students, welcome back to our class. For those who are just joining us, I'm Cikgu Hasnitah from SMK Bagan Jaya, presenting to you tonight Content Standard 4.1 Physics in a Magnetic Field. Okay, now let us continue with the fourth learning standard on how to describe the effect of a current carrying coil in a magnetic field. So we have done with the straight wire, and now let us check. Coil is actually a wire which is power supply of rotation on the coil in this magnetic field also can be determined by applying Fleming's left hand rule. Okay, so when we place carrying coil in between magnetic field, it will rotate in a certain direction. Okay, in which direction, how to define rule. Okay, so now this is our third activity to explain how current carrying coil in the magnetic fields experience a turning force. Okay, a turning force. Since we have two sides, so the coil will be turned or rotate either in clockwise or in anti-clockwise direction. So how to determine? Let us check at this activity one after another. Okay, first, you are asked to draw magnetic field line for this permanent magnet with the north pole on the left and south pole on the right. So again, you just draw. Directions of magnetic field is from the north to the south. Okay, and then second, we have to draw the magnetic field line for a current carrying coil. So for a current carrying coil, there will be two mark there. The first mark showing that current is into the paper on the left X mark, and the dot mark on the right showing that current flow out of the paper. Okay, mean if you draw a plane, so on the right side current flow out on the paper and it will enter the right side, so flow into. Okay, and this is the position of the coil we placed in between the magnetic field. Okay, on the left current flow into, on the right arm current flow out of paper. Okay, and third we have to draw the catapult field acting on this current carrying coil. All right. So how to do? So first we draw, this is the magnetic field in between the permanent magnet, again from north directed to south. All right. Okay, and on the coil, how to draw? So on the left side, current into direction is clockwise. Okay, and on the right side, current flow out of paper. The magnetic field is anti-clockwise. Okay, so this is how the magnetic field in between the coil, right? Okay, directed to this direction. Okay, so now how to draw the catapult field, student, how to draw the catapult field. So from here, okay, for this part where current flow into the current carrying coil, stronger magnetic field on top, weaker magnetic field below. Okay, on at the other side, stronger magnetic field below and weaker magnetic field on top. So from here we understand on the left side, okay, on the left side, current on the left side, force will be acting downward. Okay, force will be acting downward. And on the right side of the coil, force will be acting upward. So if you draw, the coil will be rotate in anti-clockwise rotation. Okay, anti-clockwise rotation. So we answer it is in anti-clockwise rotation, which means arm AB, which is on the left, will rotate downwards. Arm CD, which is on the right, will be rotate upwards. So the rotation is anti-clockwise. All right, so I hope you are clear with this. So how to place our finger by applying Fleming's left hand rule here. So first we place our finger on arm AB. So on arm AB, you can follow me. So this is the direction of current. This arrow show direction of current. So in arm AB, current flow into. Okay, so your middle finger should point into the paper. Okay, and then you twist your index finger pointing to the right, which is to the south. So you will find your thumb will be pointing downwards. So it is correct. Arm AB will move downwards. Okay, and then now we place our finger on the right side at the arm of CD. So how to place our finger here now in this arm, the current move outwards from C to D. So move outwards, your middle finger pointing to yourself. Okay, pointing to yourself, and then your index finger pointing to the right, okay, to the direction of south. So now you will find out your force or your thumb will be pointing in the upward direction. So we understand arm AB will move, arm CD will move upward. So the rotation is anti-clockwise. Okay. Okay, now this is the applications of effect of current carrying coil in a magnetic field we apply in a direct current motor. Okay, this is a direct current motor. It is consists of a split ring, single split ring commutator. Okay, so how DC motor works, student? Okay, where do we use DC motor? It is used a lot in small electrical appliances such as children's toy, portable drills, and hard disk of a computer. Okay, all this works due to direct current motor. And larger direct current motor we can find in machines such as electric vehicles, lift, and rollers in the factories. Okay, so this direct current motor is used to change electrical energy to kinetic energy by using the turning effect of a current carrying coil in a magnetic field. All right. Okay. So this is how DC motor operates, students. So we connect the motor to a direct current supply. So this is the parts of DC motor. A carbon brush on the right and left side connected to the commutator, split ring commutator. Okay, you can see a C-shaped ring there with an opening. So we call it as a split ring commutator. And this is the coil connected to the commutator, is placed in between radial magnet. of north and south pole. If you look at the shape of the magnet here, we are using a curved magnet or radial magnet. What is the reason? To produce radial magnetic field so that uniform force will be acting on the coil, so it always rotate in the same or uniform speed. Alright, that is the function of using curved shape magnet to produce radial magnetic field, so uniform force will be acting on the coil. Alright, okay. So this is the two important function, the commutator and the carbon brush, right? Okay, so student, how to understand the principle of working of DC motor? Let us complete this example together. Okay, first you can label the parts of a simple DC motor. Okay, first there we have the coil. We have coil A, B, C, D placed in between a radial magnet. Okay, then we have permanent magnet there. And this part is called as the carbon brush, while the final part there is the commutator, the split ring commutator. So what is the function of electric motor, student? It is to convert electrical energy to kinetic energy, or you can say to convert electrical energy to mechanical energy. And we have labeled all the parts shown in a simple DC motor. Right? Okay, next. Okay, can you name two magnetic fields which interact when current flow from A, B, C, and D? Okay, so the two magnetic field, first, the magnetic field from the permanent magnet, and second, the magnetic field around the current carrying coil. So when these two magnetic field interact, they will produce catapult field. So as the effect, we will see a turning force acting on the coil. Alright. Okay, so on diagram, show what happened to the arm AB and arm CD. Arm AB move in which direction? Upward or downward? Arm CD move in which direction? Upward or downward? So here we can apply Fleming's left hand rule. So you can work together with me. If you look at the terminal of current here, so we understand current flow from the positive terminal. So current flow from A to B to C to D. Okay, that is the direction of current, which means in arm AB, current flow into. Okay, current flow into paper. So how to place our finger here? So your middle finger pointing into the paper. And then you twist your index finger pointing to the south, which is to the right. So now here you will find your thumb pointing downwards, which means AB will move downwards. Okay, and now in arm CD, how to place our finger? So now the current directed from C to D, mean the current directed outwards. So your middle finger should be pointing to you, pointing to yourself. Okay, and your index finger pointing to the right, to the directions of South Pole. Okay, then you will find here your thumb pointing upwards. So we understand arm CD will move upwards. So in this way, the coil will rotate clockwise rotation. So to complete this statement, okay, as see there, arm AB will move downward, arm CD will move upward. So the direction is we determine using Fleming's left hand rule, and the coil will rotate in clockwise direction. Okay, the coil will rotate in clockwise direction. So are you clear with this, student, how to determine in which direction the coil will rotate, at either clockwise or anti-clockwise? Okay, so simple, just apply Fleming's left hand rule in both arms. Okay, you just check on the direction of current and directions of magnetic field. So your force will help you to, your thumb will show you the direction of force acting on both arms. Alright? Okay, next. Okay, now, okay, so after the first rotation, the coil is now in a vertical position. Okay, vertical position, which means AB below, CD now on top. Okay, since from the first, AB moved downwards, so it is now okay, uh, below. DC move upwards, so now it is on top. If you draw here, so we have AB here. This is A, this is B, this is C, and this is D. And this is the rotation, okay, clockwise. Okay, so now this is the second position. They are in vertical. So what happened to the contact between the carbon brush and the commutator in position? So you can see here, now there is no contact between the carbon brush and commutator. So the current does not flow through the coil and no turning force is produced to rotate the force. But student, you will find out the coil will continue to rotate. Okay, even though the current is not flowing. In this vertical position, the coil continue to rotate due to inertia. Okay, due to inertia, the initial motion clockwise. So it will continue rotate due to inertia. Okay, and now after this rotation, it is back to horizontal position. Now AB and CD is changing sides, okay, after the half rotation. AB on the left, CD now on the right. Okay, and our rotation is clockwise, which means CD will be rotate downwards, AB will rotate upwards. So if you check directions of current in the coil, so if you check direction of current here, so now current flow from D to C to B and to A. Okay, so this one correct. Compare the direction of current in the coil for position A and position in diagram B. So the current is now reverse. Okay, initially it flow from A, B, C, D, now from D, C, B, A, since the coil now is changing position. Okay, state the function of commutator in DC motor, students. So what is the function of this commutator, the split ring commutator? It is to reverse the direction of current in the coil for each half rotation so that the coil continue in the same direction. Okay, so this is the function of commutator. So what is the direction? The coil continue rotate in clockwise rotation. Okay. Okay then. So this is the complete drawing on the positions of the DC motor. So in the first and third position, it is in a horizontal position. Okay. In second and fourth position, it is in a vertical position. If you notice, it always turn in the same direction, either clockwise or anti-clockwise. Okay. For this drawing, current flow in this direction. So along the wire, for the left side, current flow into. Okay, on the right arm, current flow out. So how to place our finger on the left arm? So we point our middle finger into the paper. Okay, into the paper, and then you twist your index finger pointing to the right, to the south. So now you will find out your thumb pointing downwards. Okay, your thumb pointing downwards. So that's why downward arrow here. Okay, on the right side, current flow out. Okay, current flow out mean your middle finger pointing to yourself. Okay, index finger pointing to the right, which is to the south. So now here our force pointing upward. So for this drawing, we understand the rotation is anti-clockwise. So in every position, it is moved in anti-clockwise rotation. In second and fourth position, even though current is not flowing because no contact between the carbon brush and the commutator, the rotations is continue in anti-clockwise due to inertia for position 2 and position 4. Okay, so I hope you are clear how this works. motor works. Okay, now the final learning standard, linear effect, the speed of rotation in an electric motor. It is actually similar to the vector effect, the force acting on a current carrying conductor. Okay, so this is the activity in your textbook relate to this factor. Okay, so what factor effect? We have a few factor there. Okay, so first factor is the magnitude of current in the coil. Okay, when the current is greater, so the speed of rotation will be greater. Okay, second factor is the strength of magnetic field. Okay, when we use stronger magnet or more number of magnet, then the speed of rotation of the motor will be increases. And for the third factor, the number of turns of coil. When more number of turns of coil, so the speed of rotation will also increases. So these are the three factors affect the speed of rotation of a motor. Okay, again, it's shows here in this slide. So what happens when we increase the size of current, the speed of rotation increases. When we increase the strength of magnetic field, yes, the current also increases, so the speed of rotation increases. And when we increase the number of turns of coil, it will also increase the speed of rotation of motor. And the fourth factor there, increase the area of the coil. Okay, it will also increase the speed of rotation of the motor. Since by doing this, actually we increase the magnetic field, okay, around the coil. Okay, students. So this is the comparison between brushless and brush motor. Okay, brush, the similarity, both has magnet and coil. Both use magnetic force to produce the rotation. And for the differences, you can see that for brushless, the coil will be stationary, then the magnet rotates, and it is opposite with the brush motor. The magnet stationary, the coil is the one that rotate. For brushless, since there is no carbon brush, so no friction between the brush and the commutator, so it will cause no spark on the commutator, and the operational sound also will be soft or silence. It will operate in silence. Okay, while for brush motor, since there is a contact between the carbon brush and the commutator, so definitely it will cause friction. So when friction, so it will cause a spark there. It can cause a spark. So this will causes a noise or louder operation. Okay, due to the friction and spark produced. So brush motor is more noise, okay, compared to brushless motor, and also it generate more heat compared to brushless motor. Okay, then this is the advantages for using brushless direct motor. First, no frictional force, which means it is a high efficiency motor with zero maintenance and long lasting motor. But for the disadvantages, of course, it is a highly cost compared to brush motor. Okay. Okay, now student, we have done with the discussion. Let us do some practice to check your understanding on this lesson. Okay, so I have choose a few SPM past year question. So let us try it together. Okay, so you can give your response or your thoughts in the live chat as well. Okay, first question, you are given this diagram to show current carrying wire placed between two opposite pole of two magnet, and the wire swing upwards. So the wire swing outwards. Okay, so how to apply the first question, name the rule to determine the direction of force. So what rule we apply here, students? We apply Fleming's left hand rule. Okay, Fleming's left hand rule. Okay, and in diagram 7.2, we have to draw the resultant magnetic field produced. So how to draw the catapult field? This is how we draw. Okay, you draw north pole on top as shown in diagram, south pole below. So the direction of current along the conductor here is outwards, okay, to the front. So current flow outwards. So we draw a dot here showing that current flow outwards. So this is the catapult field stronger on the left, which means the force will be acting to the right. Okay. Okay, next question. We have diagram point 3. It shows a moving coil ammeter. Okay. So this is the ammeter placed in between magnet there. North pole on the left, south pole on the right. Okay, the problem is the scale of the ammeter in diagram 7.3 is not uniform. Okay, the pointer is not uniform. So what happened? In the space below, draw the correct shape of the magnet. So here you are supposed to use curved magnet, student, or radial magnet. And this will be the magnetic field in between this radial magnet. Okay, reason why we must use curved magnet, this is to produce radial magnetic field or to produce uniform force on the coil. So now it will be stable or uniform. Okay, next. You are given three choices of motor X, Y, and Z for us to build a small portable fan. Okay. So this is the diagram and characteristic you can study. So our aim is to choose an electric motor to rotate the fan blade with greater speed. Okay, so what to talk about the number of turn of coil? Okay, must use more or must use less number of turns, student? So yes, we use more number of turns. Okay, so you can write more or greater. Why? So this is to produce stronger magnetic field or to increase the force acting on the blade. All right. Okay, second factor, the number of battery used. Okay, X and Z use 3 battery. Y use single battery. So what to talk about number of battery? Better to be more or better to be less? Definitely better to be more batteries. So we write more or greater number. Why? So this is to produce stronger current, to increase the magnitude of current flow. All right. And what about the shape of permanent magnet? Okay. X using a curve shape, semicircular shape, while Y and Z use rectangular shape. Should be a curve shape, which is semicircular shape. For what reason? This is to produce radial magnetic field. Also that a uniform force acting on the coil. So the coil will rotate at uniform speed. Alright. So determine the most suitable. So we choose motor X. Alright. Okay, next. Okay, this is the final question for tonight. An example of essay question which allocate 10 marks. Okay, student, let us work together. How to take 10 marks here. So you will find this question in section B, either question 9 or question 10. So you are given a diagram shows a decorative globe floating on electromagnetic base. Okay, it is good if you can do this project at school. Okay, maybe during your STEM week or STEM day, a PBL project. So you are asked to study the characteristic of the decorative globe showed in table 1 of the electromagnetic base, then the polarity of the magnet for globe and the base. Third is the density of the globe. And last but not least is the current flow in the electromagnetic base. So here we can use a tick to pick method. So first, the number of turns of electromagnetic base, students. So better to be more or better to be less? Number of turns. So number of turns, yes, better to be more. So we tick with many. So we have 2 there, Q and T. What about the magnetic polarity between the globe and the base? We want the globe to float, student. So the polarity need to be the same or need to be opposite? Need to be the same or need to be opposite to float the globe. So they must be repel. So which means we must choose same polarity on the base and on the globe. So they will be repel one and another, and by that the globe can float. So this one, north and south, they will be attracted. There's no way the globe will float. This one, north and north, yes, it will cause floating effect. And this is south and north. It will attract to one and another. It won't show floating effect. So this one also accepted, south and south. Okay, same polarity, so it will repel, causing a floating effect on the globe. Okay, now talking about the density of the globe. So density will determine the mass. Okay, either it will be light. Okay, so we choose low or high density. Yes, we choose low density. Low density. So you take on low density. And last but not least, the current flow in the base. So should be greater current or low current. Think logic, student. So we choose high current. Okay, so you take. So all high here, no problem. Here all high. So can you see the best answer now? The best choice is Q, which fulfill all the characteristic, which means our final choose must be Q. Alright, so how to interpret this in your answer? So you can prepare a table with 2 column, characteristic and explanation. So you write back all the characteristic first. So first, number of turns, we choose many. Okay. Reason, to produce high electromagnetic force, to produce greater force. Yes, greater, many. Correct, Jimmy. Floating effect, the polarity must be same between the globe and the base. So either you write same, or it can be north and north, or it can be south and south. Okay. Reason, so it will repel each other. Okay, it will repel each other. Density of the globe, it should be low. Why? So the mass will be low, or the globe will be light. So more easy for it to float. Okay, and the current flow, so we choose high current. Okay, greater high current, so that it will produce a high electromagnetic force. So which one is the best choice? So we choose Q. And you can write back all the explanation or characteristic for Q. So on the left, the characteristic will be your first, third, fifth, and seventh mark. On the reason will be your fourth, sixth, and eighth mark. Mark 9 for your correct choose. And then mark number 10 for the combinations of answer. All right. So I guess that's all for tonight. We have discussed 4.1, force on a current carrying conductor in a magnetic field, and also some example of questions SPM this session until now. And again, don't forget, student, to get your PDF copy for this lesson. You can download and print them all for free. So, cikgu rasa itu saja untuk malam ini. Terima kasih kepada semua yang mengikuti. Cikgu mohon ampun dan maaf sekiranya ada tersalah silap kata sepanjang cikgu berkongsi ilmu pada malam ini. Sesungguhnya segala yang baik itu daripada Allah, segala yang kurang itu daripada kelemahan cikgu. Dan terima kasih kerana bersama-sama dengan Cikgu Hasnitah pada malam ini. Semoga kita berjumpa lagi di masa akan datang. Jangan lupa minggu hadapan kita akan kembali Cikgu Rosemawati pada pukul 9.30 malam. Bab 3 graviti, iaitu hukum Kepler. Okay, 3.2. Kemudian pada hari Ahad, hari yang sama seperti hari ini, pukul 8 dengan tajuk. So, semoga kita berjumpa lagi. Teruskan sokongan anda kepada Akademi Youtuber dan kita jumpa lagi dalam siri yang akan datang. Okay, Assalamualaikum dan terima kasih semua. Bye-bye dan jumpa lagi.